On this adventure in algebra, we're going to study the second isomorphism theorem and some applications. So here's the statement of the second isomorphism theorem. You're given a group G, and you're going to consider two subgroups. H is an ordinary subgroup, and N is a normal subgroup. Then Hn is a subgroup. H intersect N is a normal subgroup of H, and H mod the intersection is isomorphic to Hn mod N. So I tend to think this statement has a lot to unpack. We have to remember this set Hn is just all elements in G that can be factored as little h times little n. Some h and h, some n and n. And so we already saw a set like this when we discussed direct products. In general, this set is not always a group, but when n is a normal subgroup, this set is. And one thing that wasn't clear is that H is a subset of Hn, and n is a subset of Hn, because these are examples where you set one of these factors equal to the identity element. I won't lie, the number of times you end up using the second isomorphism theorem is not that often, but in more advanced treatments of group theory, it does get used, normally for certain types of induction arguments involving what are called CELO subgroups. So in this case, I'm going to actually do the proof so that I don't have to do the proof in class. So how do you prove this result? Well, there's three major steps. Actually, there's two major steps. The first step is to prove this result. And then the second step is to apply the first isomorphism theorem to a cleverly chosen homomorphism to get the second result. So first we're going to show Hn is a subgroup of G. So what do we need to do? We need to take two elements and another two elements, H prime, N prime, and we need to look at the product. So the product looks like Hn, H prime, N prime. We want to show it lies in this set, so we need to be able to rewrite it to look like the product of something with H times something with N. Apparently it doesn't look like it. And so the way to do this is to take advantage of the fact that N is normal in G. So the problem here is we can't move the H prime past the N. But because N is normal in G, we know that N H prime is equal to H prime capital N, which tells you that little n H prime is going to be equal to H prime N double prime. So let's use that fact here. Hn H prime N prime is equal to H prime N double prime N prime. If I group the H terms together and the N terms together, then it looks like I have an element in H times an element in N. Congratulations, I actually have something in the subgroup. Of course, I also need to show inversion. So I need to look at the inverse of Hn. Well, normally that's N inverse H inverse. But again, I need to be able to rewrite it as an element in H times an element in N in the right order. So again, Since capital N H inverse is equal to H inverse capital N, we know N inverse H inverse can be rewritten as H inverse times N dagger. For some N dagger in N. So substituting that in here, got H inverse N dagger, which is in the set we want. So we're closed under multiplication and inversion. Those are the two steps we need to show something is a subgroup. It's also not hard to see that N is in fact a normal subgroup here. Why? Because N is closed under conjugation by every element of G. So it's certainly going to satisfy the same property for these special elements in G. So then the main step we have to do left is the rest of the isomorphism. And so the idea is to construct a homomorphism instead. And so remember and so what I'm going to do is construct a homomorphism from H to Hn mod n with the kernel of phi being equal to H intersect n. If you can do that, then by the first isomorphism theorem, and surjective. I should add that part. By the first isomorphism theorem, you automatically get that the kernel has to be a normal subgroup in the domain, and you have to get that H mod the kernel is isomorphic to the image, which if you're surjective is the whole codomain. So we just need a homomorphism with these two properties. And the homomorphism is a simple one. Or let me use the identity element. The identity element is an element in N. So here's my product in Hn. And here's the corresponding coset in this quotient group. What are the things I need to check? I need to check that phi is a homomorphism. So look at phi of a product. Well, by definition, that is going to be Hen times H prime En. Well, that's just by definition of multiplication, H prime N. But that's exactly what we're going to get from phi of H times H prime. So we are homomorphism. We also need to show that we're surjective. Let Xn be one of these cosets. Then, of course, that means X has to be equal to Hn for some H and H, N and N. But then Xn is H little n n. It's just little h capital N. The point is these two cosets are the same, because little n is already an element in this subgroup. And so phi of H is Hn, which is Xn. So it is surjective. Finally, we need to show that the kernel of phi is equal to H intersect N. Well, H is in the kernel of phi if and only if phi of H is the identity element in Hn mod n. But what is phi of h? It's defined to be Hn. And that should be true if and only if h is an element of n. Note here, of course, h has to already be an element of capital H because you're looking at elements in the domain. So if I did this correctly, this would have been h in h such that all the way down, and then you'd see, well, then this tells you h has to be in this intersection. And so the kernel is actually equal to the intersection of h with n. And by using this if and only if approach, I managed to get subset inclusion both directions at the same time. And so there's the second isomorphism theorem. The way I always remember this proof is that you always define the homomorphism where the codomain is the uglier group. And frankly, to me, Hn mod n looks like a much harder to understand group to me than H mod H intersect n. So picking this as my domain, this is my codomain, is a lot easier than picking this as my domain and this is my codomain. Particularly since that latter step also requires more work, because then you actually have to show that this is a group by showing that this is normal. So this approach has the advantage of avoiding that extra work. So an example of an application is that for n bigger than or equal to 5, if n is a normal subgroup of the symmetric group, then n is either the trivial subgroup, the alternating group, or all of Sn. So why should this be true? Suppose not. Then by the second isomorphism theorem, and intersect An is a normal subgroup of An. But it's a fact, proven in the book, that An has no non-trivial normal subgroups. Which means either n intersect An is equal to An, or n intersect An is the trivial subgroup. In this case, you now see that the alternating group is a subgroup of n, which is a subgroup of Sn, but remember that would imply that the orders have to divide each other. By Lagrange's theorem, and we have a bit of a problem. These two only differ by a factor of 2. So either the size of n is going to be equal to An, or the size of n is going to be equal to Sn. There's really no other number that's in between these two numbers that satisfies this divisibility criterion. So then you just have this case to consider. What happens when n intersect the alternating group is the trivial subgroup? Well then, using that second isomorphism theorem, here we're, by the way, second isomorphism theorem the role of H is played by this alternating group, I now see that I'm saying that AN modulo N intersect AN, because it's the trivial subgroup that is just the alternating group. By the second isomorphism theorem, that's equivalently AN times N mod N. So of course, again, we have AN is a subgroup of AN times N. If we assume it's a proper subgroup, not equality, then that would imply that this group has to be Sn. Which means that this quotient has half the permutations, but the numerator contains all the permutations. So, by order considerations, n has size 2. So, if n has size 2, then n must have the identity element and some permutation whose squares to the identity, which means that it is a product of disjoint 2 cycles, disjoint transpositions. But it's not hard to see that there's no way that that is going to be normal as well. Just take whatever's in sigma 1, A1, A2. Now just conjugate by any permutation so that you end up with A1, A3 times the rest. We know that should be possible. And while that's going to give you a new permutation of order 2, that's not sigma because it's got a different 2 cycle. And it's not the identity. So in particular, it's not an element in this subgroup. Hence, n is not normal. So other than cases where n turned out to be the trivial subgroup, the alternating group, or the full symmetric group, we couldn't find anything else. And we see that the main steps in the argument actually use the second isomorphism theorem. And if this is a hard proof to follow, that is perfectly understandable. This is a bit harder than what one normally finds at this level in this course. But I wanted to give an application of the second isomorphism theorem, and usually applications of the second isomorphism theorem are on this level.